All right, chemistry, this is your video lecture for Chapter 7, Section 2. We are talking about oxidation numbers. What you should be getting out of this video lecture, you should be able to list the rules for assigning oxidation numbers themselves. You should be able to give the oxidation number of each element in the formula of a chemical compound. And you should be able to name binary molecular compounds using oxidation numbers and the stock system. So let's start with what oxidation numbers are. They are assigned to atoms composing a molecular compound. Okay, this is the most useful version is when you use it on molecular compounds, or a polyatomic ion, again covalently bonded, that indicate the general distribution of electrons among the bonded atoms in the compound or ion. Now remember, when you have anything that's not a pure covalent bond, a nonpolar covalent bond, you're going to have uneven distribution of electrons within that bond. They're going to be leaning more closely towards the more electronegative atom. So we have several rules that you're going to follow. These are also going to be found in your textbook, but you're going to need to have this list, this in the next slide, out for reference as you work through these problems. First up, the atoms in a pure element are assigned an oxidation number of 0. A pure element is anything like the diatomic molecules, right? If you have O2, F2, I2, if I have a molecule of oxygen, okay, the oxidation number is 0. You're going to assign 0 to each of those oxygens. Number 2, the more electronegative atom, which is the thing that's going to be listed second, okay, the more electronegative element in the binary molecular compound is assigned the number equal to the negative charge it would have if it were an ion. Now, it's not an ion because this is a molecular compound, but if it were an ion, if it were, the oxidation number you're going to give it is equal to that negative charge. Step 3, fluorine, because it's the most electronegative element on the periodic table, is always going to have an oxidation number of -1 because it is, again, the most electronegative element. Step 4, oxygen has an oxidation number of -2 in almost all compounds because it's the second most electronegative element on the periodic table. The only time it's not going to have a -2 oxidation number is if it's in a peroxide or if it's bonded with fluorine. Next set of rules. Hydrogen can have an oxidation number of +1 if it's listed first, but it can also have an oxidation number of -1 if it's listed second in the chemical formula. Number 6, the algebraic sum of all of the oxidation numbers in a neutral compound is equal to 0. Okay, so unless it's something that has a charge, okay, if it's a neutral compound, all of the oxidation numbers need to cancel each other out. Number 7, the algebraic sum of an oxidation number of the oxidation numbers of all the atoms in a polyatomic ion need to equal that ion's charge. Okay. Number 8, oxidation numbers can also be assigned to atoms in an ionic compound. You can actually talk about the stock system and assign oxidation numbers. However, it's not all that useful because, again, those are whole charges. We don't necessarily need to have this oxidation number to tell us the general distribution of those electrons because they are on those anions. So let's practice those rules. Okay, so we're going to start with the second element here with water. It's oxygen. It's -2 in most things. Okay, and so in order to balance out that -2, each of those two hydrogens needs to be a -1. Again, start with the most electronegative atom. Give it that -2. Okay, the second thing I'm going to look at is actually hydrogen because it's only going to be a +1 or a -1. But this here it's listed first, so it's going to be a +1. There are 2 of them, so in order to balance out my positives and negatives, sulfur needs to be a +6. And I hope you notice that the charge on sulfur is never a +6. So oxidation numbers and charges must be different. Moving on, dinitrogen pentoxide. Oxide is going to have a -2 oxidation number. In order to balance out, nitrogen is going to have a +5. Moving down, I have an ion, so my overall oxidation numbers need to equal a -2. Okay, so I have an oxide there. That's the more electronegative of the two, so I'm going to give it that -2 because that's the charge it would form if it were an anion. And in order to have an overall -2 left over, that sulfur is going to have to be a +6. Using the same strategy for this phosphate here, I look at the most electronegative atom, which is oxygen, give that -2. And in order to have an overall oxidation state of -3 like the phosphate does, that phosphorus needs to be a +5. Here's another set of practices for you guys to try. Go ahead and press pause and see how many you can do on your own. Again, please refer to the list in your notes. This is not the time to try to memorize that list. Have that list out while you try these. Please press pause now. All right, let's see how we did. Go ahead and check your answers. Alright guys, that's going to do it for this video lecture. I know it's pretty short, but really all we're doing is we're describing where electrons are within bonds, and we're using oxidation numbers to do that. And there is a very simple, spelled out process for you to do that accurately every time, printed out in your notes and your textbook. Be sure to reference those as you work on your sample problems. Alright, chemistry, I will see you next period.